get to the element in those lists. So if I would like to operate, for example, um, on the, I will create a second list, string all texts. So those are the output texts. And I would like to go through the input lists and check for the string which will be, for example, equal to 3 or 4. Then I will be able to do it. Although I will be able, for example, to sort this list, and I will be just able to just take, for example, all text, or let's make it maybe like this: string text 1 equal to texts third. So now I'm able to take the third item in the inputs. When I had here an item, I didn't, and the beginning of the code was different, of course. I wasn't able to go for the specific element in the list. So although the algorithm was working, the whole component was working, I was not able to, this one is not really necessary. So giving here list as input type will open our components to operate on those lists properly. Also, I think it will be a little bit faster when you are using a list here, because the component doesn't have to go every time he has a new element in the list again and again. He just knows that this is a list, and okay, I can operate already on this list. So I will run this code. I will type Grasshopper. And I will go into the first plugin. Now you see that already he see that this should be a list. But also again, if I will, although it is he now have a problem because he doesn't see the element with the index 3, which is generally a good way to see the Visual Studio break the solution in the place which caused the problem. So it's also a great advantage of using Visual Studio, because we can test in which part of the code something is not going right. If I will continue and I will just deliver the list which will have at least 3 elements. Yeah, I have to, like you remember, change it to the multi-line data. He is able to find the element with item 3. If I would, again, if I would like to go back to the plugin which was on the beginning, and here was the item, I was not able to take the specific element from the list. So I have just, although the plugin was working, I didn't have the wide range of methods which I can apply to the input. Okay, but this is generally a question from the audience, so I hope I solved at least partially the problems. I will stop the solution. I will stop also the Visual Studio for a second. And soon I will give the, in 10 minutes, I will give the screen to Sfera to let him introduce you to the component which we will be doing today. But before we will do the this component, I will just I want to share something with you, which is generally my thoughts about why and what we have to about what we have to think when we are creating a plugin. So first of all, when we are using Grasshopper, and even if you are using a visual programming, not the C Sharp, and even in the basic code in the Grasshopper, before you start the work, don't think about what kind of the tools you have to use. It's better to just think what is the input, what is the variable. Sorry for the and what is the output. So it is much more important to first give those three. Just take the piece of the paper and start to think what will be the input, variable, and output. And of course, on the beginning, you will have a problem to describe properly those elements, and you will need some time to be familiar with this approach to the design. So normally, when you are using Revit, AutoCAD, or ArchiCAD, you generally have a model which you have in your head, and you are just drawing from the left to the right, from the general to the local, from global to detail. You generally are doing as fast as the model is appearing in your head, then you are creating the model. Unfortunately, in the approach with the algorithm I did design, it's much better to first sit down, do not do anything, and start to think what will be the input, variable, and output. And especially the variable, it's something which is really which you should think about. So, for example, if you would like to create a component which will be very quickly creating a building, then you should start to think how I want to control this building to be done. Because if I will do it like we did it in the last 3 days, that we are starting from the let's create a grid, then let's define the height of each floor, then let's create the span, let's define the span, and so on, then suddenly you finished with too many variables at the beginning of your code. And this is very common mistake that people start to make, that we can parameterize everything in our code. Of course we can, but then our code will be just unuseful. So it's very important to set up the variables which will be the primary variable and the secondary one. And it's also super important to find the variables which can be described as a rule. So I would call it automated variables. So today, and when you will think about how you want to control the building, today we will, for example, try to figure it out how to make a component in which we just declare the boundary, geometrical boundary condition for the BREP, and this BREP will be populated with the building, I would say. So in this case, you will not have to specify directly your variables, every variable. You will be just have the primary variable, which will be the boundary of our building, and then you will have a secondary variable, which will try to make as a some additional class settings, which will be responsible for delivering to the code the information about the specific items. So I hope I hope today we will um, finish somewhere after the lunch, and then every one of you will try to make a little bit different variant of the code which we will give you. So we will build the code till the lunch, I hope, maybe a few hours after it, and then all of you will try to adjust the code to your needs. So if you're an architect, then maybe you would like to add also some parametric facade to the code, which to the model which we will be able to create. Some of you maybe will look for the analytical model of the building. So when you will be doing the code today with Sphera, try to think how I could generally modify this code to your needs, and then we can discuss it together how you can do it. So try to follow Sphera, but also try to think now about how I can generally modify the code delivered by us to your needs. So Sphera will take now the screen.
Good morning. I think you can hear me. So as Marcin said, today we will try to, I'll just share the screen with you. We will try to create a run component, which will create a building inside a BRAP. So just give me a second to share the screen. Can you see my screen now? Please, somebody just raise their hand if you can see it. It seems fine. So as I said, the objective today is to create a plugin containing 3 components, which will take this randomly shaped BRAP and turn it into a building consisting of slabs and columns, much like we've done in the previous 3 days. So hopefully we'll not learn too much new things today. We'll just try to sum up things and you will try to do it on yourself. And we will, of course, be able to help you along the way. So I'm thinking before lunch, we will try to establish everything inside this framework and the component, and then you can try to create the methods for yourself after lunch to make everything work. We will see how far we get before lunch. So I try to sketch it up. Like Marcin said, we want to think about how we want to assemble this component. So we will create 3 components, and the main one is the middle one, which is the create building. And this should be able to just take a volume object or a BRAP along with some properties. And from this, you will create a class like you did for a column with Marcin yesterday. And this will not display anything. It will just be a class of a building. And we need a second component in order to break it down into BRAPs, which is displaying it in Grasshopper. So just a quick recap of the classes. I found it difficult myself sometimes, so I tried to think about how we can make it relevant for a building. So yesterday you did a column class. So if you think of a building as a class of its own, a building can have several properties. It can have some ventilation, it could have a room organization, electric installations, building physics, installation, thermal properties of windows. And of course, since there are most engineers here today, you have the structural plans. And today we will just look at slabs and columns, which in themselves could be classes as well. So we will try to make kind of a framework here where we will define a building class, which is the main one. And this can, of course, have levels. And you can add here, like Marcin said, if you're an architect, you can add a facade, you can add whatever property you want, really. And then we will have a level, which each level then, from a structural perspective, could contain some slab and then some columns. So I try to sketch here the properties and the type of property. And then again, you have a slab and a column with some properties again. So I think we will start today by creating these classes for creating the properties. So I think we can jump into Visual Studio and we should just try to make everything from the beginning again. So if you open Visual Studio with me, and remember, open it as an administrator to be able to store the files that we create in the Rhino folder. Okay, so new project, and we can search. I reckon everybody has downloaded the Grasshopper, and I had some questions yesterday, so it's important there. You can see we have two different templates here. Remember to select the one where it's C# and not Visual Basics, then you will have problems. So you can select the C# one, press next. The project name could be building creator or something you can choose. I will create this, and you will get this for the component. I think the first component can be, we can just leave it like that. We will add the descriptions later on. So finish that. So are everybody there? If anybody has a problem, please raise your hand and Martin will help you. Yeah, okay, so I guess we're ready. So we can start by just changing where we will place it. So I can change the name to create building for this main component. Nickname, not so important. Description, you can add later. And if you want it now, you can add it in the same folder as you did yesterday. So you can make it for PC 2021, which will be the folder that it will appear in Grasshopper, and a subcategory can be your building or something. And before we start with registering the input and output parameters for this component, we will start with the classes. So if you have your Solution Explorer on the right side here, I'm just right-clicking here, add a new folder. I will rename that and call it classes. And if some of you don't see the Solution Explorer, you can make it appear by going to View, and you see here that you can select it, and then it will appear here. So if you don't have it, you can find it here. So in that class, again, I'm right-clicking, add, and I want a new class. And I will call the first class building. Adding that. So we will start with the building, and let me just get the PowerPoint for you again. So the building, you went through this at Marcin, so let's just make a quick recap. A class will have some properties, which are listed here, some constructors, which make an instance of that class, and some methods. So we will start by just creating the properties and some constructors, and later on we will have a look at some methods for it. So I think yesterday you just made something like this, a double and a name. But Normally in a class like this, you won't be able to change it from outside the class unless you're allowing it to. So we will try to make it a little bit different. So you can do, did you go through encapsulations yesterday? No. Okay, so just a quick example. So if I write, I think you wrote public with Martin yesterday. He mentioned something about it being how other components or files outside of this class can access it. So if I name something public and string, and I call it name, which is a property, then I can find for outside in here, for instance, to get the building. So we need to reference it since we put it in a different file. So in the using here, you need to add build creator dot classes. So then we will access the files in this folder. So if I go down here again now, I have the building class. And I can probably find the name from, no, so. I just initiate a new building. Then I have building dot, and I can find the property here since it's a public property. If I change this to private, I can't find it anymore. So it's protected inside here, meaning that I can't change it inside another file, which most often is a good thing because you want to do that, or you don't want to do that by accident. So what we will do is we will create a getSet property. So if you type public and name, sorry, public, and it's a string, the name, and I use capital letters. And then you make some curly brackets here. So it's actually a private string now, but you make it public by typing get and set keywords. So with these now, I can find it again. I will go into the component again, building, which is my instance of the building class. And you can see that I have a property named name. So when I use the get and set keyword here, I can say that name equals building, and I will change it. Or if I just use it, I can get it by saying that string the name equals building dot name, and then I will retrieve it, that information. So if you want something to be available outside for to set it, you can use the set, or if you just want to be able to get it and not changing it because you want to protect it, you can just use the set keyword. So for now, we just leave it with the get and set. So there's the first property, and the next property we want is a list of the levels of the building. So we create the level here, levels, and I'll just copy and paste. So this. So this one will be a red line under now because we haven't created that class yet, so we will do that. So again, right click here, add a new class. Class, I will call that levels. And again, we have a public string, which is the name, curly brackets, get set. So that is the first property. The second, or just leave it with the name for now, and you can see now. Sorry, just change the name to make it consistent. We would just want one level as a class. Press yes, let it change it for you. And if you go back to building, it should be green, meaning that we have a class, and it should work fine. So we have the building, we have a name, and we have the levels, which is containing. So next we want to add some constructors. So this is properties of it. Then we will make the constructors, which are where we create an instance of this class. So the first one will just be public and an empty one, which by default is created, but it's nice to make it as a good practice. So this won't do anything. It will just assign it, and then you can add, for instance, the parameters and levels later on if you use this constructor. And we can create another one, public building, which takes some input, and we can take, for instance, if we want to assign the name. And I'm using an underline and small letters when doing this. And then we want a list of levels. So sorry again, should be 1L. And then we want to assign these inputs from the constructor to these properties. So then we can just say that name equals name and levels equals level, like this. So that can be our entire building class for now. And if you want to, you can add more later on, as Marcin said, but this is what we need for now. And we can create a new class, which is the column. Yeah. So if somebody didn't make it, I'll just copy it for you. So again, you have the properties, you have some constructors, and under here, you can have some methods. Let's try to make a method quick. Let's say that you want to make or get the amount of levels of the floor or on the building as a properties. So then we can make it public, meaning that you can exit it from outside, and it will be an integer since it's the number of elements in a list. And let's call it get levels. You don't need any input for it. So the only thing that you want to return is levels, which is the property here, dot count. So this method here will return the number of elements in this list. So if I go back here, you can see that if I type building, which is just the class, dot, and I have a method here called get levels. So you can create more of those if you want to. So get levels, and that will return, as you see, an integer. Oh. Oh, Marcin is typing as well, so I have to. He has to keep up. So I can post, or you can make that. And do you get the point with methods, or should I do another one? Because I was thinking that you could try to create your method, give you 15 minutes, or sorry, class. You can try to create a column class like you did yesterday, but this time with a slight change of parameters. So we can start on it together. We can do right click again. You want to add a new class, call it column.cs. You have some properties. So I will pick up, I think I have it there. Yeah, I will upload this to the mural, but for now you can see it here. So try to create this class with these properties. So you want to give it a name, a height. The center is an array, and a cross section, and a material, and just two constructors, an empty one and one which takes the height, cross section, diameter. We're just for now assuming that you're only having circular columns, a center point, and an ID. So try to create that. And I will continue at 9:50. If there's any questions, you can just ask and we will help you. Okay, I'll continue. Did anybody make it? Please raise your hand if you came close at least to creating this class. That's great. There's a lot of hands there. So I'll just do it quickly with you, and for those of you who didn't make it, then I'll just post it. So again, we're creating these get set properties. So string first, just the name, curly brackets, set. Just copy this. Then we want a name. Sorry, the height. Then we want a cross section. A center point. And here, as I said, we want an array. We'll come back to that later, but type it here. So it's an array of the x value, y value, and the set value of the center point instead of using the Grasshopper or Rhino classes. And finally, we can add a string for the material. So then we want our constructors, which is just a public, just a name, an empty one. And then we wanted one which takes double height center point and the ID. So just assign those to the input. Like this. So I'll paste that for you. So we now have a column class. We have a building class. So next we will create a slab class. I posted it so they can. Okay, I'll give Mars in a minute to create it. So all the components or the sketches should be mural. So if you want to get a head start, you can start on the slab component if you want to. So then again, just click classes, add and a new class. So you can start on the slab if you want to. Yeah, I think I'll continue. So a new class, add, and this one should be a slab. So again, we have just commenting to make it easy, properties, constructors, and methods. So again, this slab should have a name. Just using a string, ID. And a get set. And we want the material of it. As a get set, we want the thickness as a number. And finally, we want a brep representing the area surface. So slab geometry. Again, as get set, as you can see now, can't find any class named brep, and that is because by default the classes doesn't reference the Grasshopper library. So we can just go into the main component and copy these two and paste it here. Don't need those, so there you have it. You can find it now, so we have every property that we need. So, and again, constructors, creating classes is quite repetitive. It's very much the same for everyone, at least the setup. So an empty one. And one which takes the surface, which is a brep representation of that, a string for the material, the thickness, and the idea. Curly brackets, and assigning those to the parameters or properties. So idea, material, thickness, and slab geometry. So that's the slab class. Just leave it here for a minute. Before we start on the levels. And as you can see, I'm leaving the methods empty for now, so we can, if we have time, we can go back and have a look at that. So I think I'll continue. So I'll go back to the level. And for now, we just created a string here with the name. But for the levels, we want also some columns, which we will assign to that level, and a slab. So since there are several columns on each level, we want to make a list containing these columns and only one slab, so that can just be a slab. So again, public list level, Oh, so there should be columns here. Sorry. Call it columns and a slab. Calling it slab and get set. So again, an empty constructor first. And one that takes a slab, and string ID. So this one we can use, for instance, if we have a roof where there are no columns on top, you can use this one. So the only thing there is a slab and the name. Oh. It's warning me when I'm using. No, it's not. Yeah. We can use a small letter here. It's not. It will work both of them, but it doesn't like it when you use the same name for a class and a property. So we just change that. And finally, a third constructor for this one, level. So a slab, a string or a list of columns. And a string. The slab. Like that. So we have the main class, which is the building, which contains a list of level. Then we have created the levels, which has a list of columns and a slab. And finally, we have the two bottom ones, which is the slab and column. So I'll go back to the level, give you a minute to look at that. So are there any problems so far, or are you following it to this? If there's any problems, ask a question privately or in the chat, and we will try to have a look at it. Or otherwise, we will start to create our components. Okay, I guess everybody's following to this point. So we have our classes. I'll just close this for now. And we can begin on our build creator component here. So we'll start with the input parameters. Oh, sorry, we can save it and we will just fix the properties here and make sure that we're opening in it or building it in the correct folder. So if you right click on a build creator, go to properties, and in the build path here, you should find the Rhino folder. It should be in C, program files. And you can should find Rhino here somewhere. There it is. The plugins, just copying that file path, pasting it here, and saving. So if we go back to the PowerPoint again, I see there was a question. How you fixed it? Oh yeah. Are you fixing it, or should I? Oh, you answered. Okay, that's good. Okay, so back to the PowerPoint, and we will look at the components. So the create building component should have a list of, I changed it to doubles, but just a list of the properties, which is Marcian mentioned, is our secondary parameters, and as brep, which is the volume that we will create the building inside. So P manager. Yeah, I can show the file path again. So I just right click, properties, and the output path here you can find, if you go to the disk C, unless you have some special place where you save it, if you just follow the automatic installation, you will find it here. You will have program files, and you can browse down, and you will have Rhino 6 in the program files. Here we have a plugins folder again. So I'm just entering there, and here you can see there's some different components which are created before and a lot of secondary files. So just select that, Control C, pasting it in the output path and saving. Is that okay? Great. So back to the input. As I said, we will have two inputs here. First, the brep. So add, and we can find the brep parameter here. So we have a string for the name, the abbreviation, the explanation, and finally we have the param access, and we will access that as an item. Semicolon, and just typing 0 here to make sure that be consistent with later on. This is the first input. So this will be a brep. Some description here. Second input will be a list, and it should be numbers. So add number parameter, string, 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 param access, and this time list. And second input with index 1. Okay, so that is the input. The output will be just an instance of our building class, which we'll create. But for now, since we want to test the components a little bit, just add pmanager, and you have something called generic parameter, which in general handles all types of data. So if you change the output later on, we don't have to change it here, and then we will go back finally and change it to we need a generic anyway, since we're outputting our own custom class, so we can use this all the way actually. So string again, string, h, param access, and again an item. And this is the only input. Yeah. So I printed or copied the input and output to the chat. So if you missed that, you can use it. So we continue within the solve instance. And the first thing we have to do, I like to use something called regions when I work to make it easier to keep a track. So if you add a hashtag and you start typing region, just enter that, and then another hashtag and an and region. And I can name that assign input data. And you will see this small option minus sign here where you can close it, so that later on when we get a lot of code, you can divide it into different groups, which just keeps things tidy as the code grows. So first we have to assign some input. So we have a brep, which is the boundary, and we just have to create a new brep, which is empty, and that is input 0. And then we should have a list of numbers or double, which is the settings. Again, a new list, which is the second input. And then we'll try to get to reference them from the input, and I'm using an if. So if and then not. We're trying to get some data here. da.get data. 0 is the first input, and it should reference, again, when it's just one element, you have to use the ref keyword to this. So this will try to get this, and by default, the output of this command will be either true or false. So if this is false by using the not, we don't want to run the rest of our code, so we just use return. So if we can't get any boundaries, we don't want to run the rest of the code either, so this will do that. And we can use the same thing for the next. So I'll just copy this, paste it, and since it's a list, we need to use get data list. It's the second input, and we want to reference it to the settings.
Can I comment on this code for a second?
Yeah.
If you take a second, because previously after if statement we also always were using capital brackets, but if you just have a one line of code after if statement, you can always use you can use it without the capital brackets. But in general, after if statement, you can use capital brackets, and maybe it should be here also that after if you have a capital brackets, inside there is a return with the semicolon. This is nothing new. It's just that you have to remember that if you just have a one column after if, it will be automatically written, but it can be done like Sphere is doing it right now. So yeah.
Yeah, so like Martin said, we can use it like this, but it's just to save time, but I can keep both here. So you will see what it's doing. So that's the settings, and we will try to get from the settings. I'll just go back here. So we have some different secondary properties, but for now, just assume that we're not using them. So we will just get settings later. We just want to try to run our code. Or now we can make it, it's faster than you can try for yourself later. So we will create a new component. So now I'm just right-clicking anywhere in the Solution Explorer. So right-click on the build creator, add a new component down here with the class. And you should have the Grasshopper component under Rhino zeros. And I will call it building parameters. So this is the first component, which should be quite easy to make. The only thing that it should do is it should take some different numbers as an input, and it should collect them in a list which we will input to the main component. So here we need some number parameters. So pmanager dot add number. And an item. And a new trick, if you didn't see this earlier, after the item, you can add a second input, which is a number in this case, so that if you don't input anything into your component, it will have a default value. So you can see it here, it's a double, and it will be the default value. So if you don't change anything to your component, this number will then be used. So if you use this on every input, it means that we don't have to create a slider or a panel to put some input into our building parameter component to make it run. So it will be much easier to just run it by some default values, and we will save a lot of time. So you will see that later. So just add 300 here. This could be the default floor height, for instance. And we are using centimeters to be consistent with the previous days. Something like this. And we will have 5 of those. So I'm just copying this. 2, 3, 5. And we want the floor height. We want column diameter. So let's say set this to give it 30. Change this. We want a slab thickness. So say I can just set it to 30 as well. And we want column spacing, or the distance between the center point of each column, in the x direction, and we want the same in the y direction. So say 5 meters for both. So we have 5 input parameters as numbers, and then the only input should be a list where we just assemble those together. So P manager, add again a number parameter, and this time a list, and this is the only output here. So I'll just copy that for you. So we have our input, we have our output. So the final thing to do is just to create a list of that. So again, just to give you a training, I create a region, assign input, and region. It's not really necessary here, which is just short code, but it's nice to see. So a double, just the height. By default, it should be empty. Ooh. And I'll just copy that 5 times to save some time. Slab thickness, spacing in X direction. And spacing in Y direction. So these are the 5 inputs that we have, and then we'll assign them. So da dot get data, and this time we don't want to return if there's not any input. So I'm not using the if or the return here because we have some default values which we want to use. So ref, the first one was this floor height. And just copying this to save time. 3, 4, 5. Change indexing and the name. So if you double click on a parameter like this, it will mark the whole thing. So you can just double click, Control C, double click, Control V. Like this. So that should be everything. So we have created variables. We have assigned the input to them. So the final thing to do is just to create the list. So a new list of doubles. So just the data, new list double brackets. Then we just want to add everything here. So data dot add. Again, I'm just copying this to save time. 4, 5. Double click. double click, Control C, double click, Control V. So now we have a list with every input parameter. So the final thing that we need to do is just to assign this to the output. So da.set data list 0 index is the only input we have, and then we want to assign data to that and semicolon. So this is our entire code for this component inside the Solve instance. I'll copy it for you. So did everybody make this component? Just raise your hand if you did. Yeah, good. So we have made our first component. So then we can get the settings from here as parameters inside our main component. So we have assigned the input. So get the settings, and this is the double floor height. And that is the first element of that list. So this is the list now. I can change, we can just keep it. So settings, and the first element, so just square brackets and 0, which is getting the first element of that list. And just copy this 4 times. For the second one was column section, yeah, column diameter. This was the slab thickness. This was spacing X, so just call that dx. And we'll call this Y, and it should be 4. So we now have taken everything from this list and created variables inside our main component. So that was the first assign input data region. And I'll just create a new region here. And an AND region, which will be the main part where we create the building. So the first thing we want to do, or should we give them a break? We would do. Yeah, I think we will take a break. So should we say 15 minutes? 40, okay, 12 minutes. And yeah, any questions? Just chat us. I'll just get a quick coffee, but then we'll be able to answer, and we'll see you at 10:40. Okay, so we're back. Yeah, before the break, we created our classes. We created the building parameter component, and we set the input and output for this main component. So before we start again, we just have to create or assign the building parameter component to the correct folder. So if you just go to the build creator component, and the location here was just the PC 2021, which you use later there as well, and second folder, which is your building, just copy that and enter it here, so that they will be in the same folder, making it easier to find. So with every class and ready, we can start thinking about how we will create our building. So I tried to make a little drawing out of it. So we need two components for this. And the first one is that we want to create the levels. We want to find the levels of each floor within the BRAP, and we want to place the columns there. So we will start with the create levels method. And the way we will do that is by finding first the height of the entire BRAP, and then we will see how many floors we can place within it without getting outside. And then we will create or use a function in Rhino, which is called a BRAP plane intersection. So we will create a plane at each level. And at those plane, we will find the intersecting surface or curve between that plane and the BRAP. So I think we will start there. So as you saw with Bungie, at least yesterday in the C#, you have the main solve instance space, and you have a space below here. So we want to use the space below to keep the actual solve instance kind of clean. So we will create our methods here. So we can name this private because it's only going to be used inside this component. So we don't want any other files to have access to it. And what we want is a list of surfaces which are by default BRAPs, or every surface is a BRAP. So we'll use the BRAP here, and we will call it create level surfaces. And the only inputs that we need is the BRAP, which is the input BRAP, which was the boundary. So here I will just call that B. And we need the floor height, or the height of each floor, to find the number of divisions that we can do. So within this method, I use square brackets, curly brackets, and you can see now this is red, and the reason for that is that we have an output from it, but if you hover it, it doesn't return anything. So just to get rid of that, we can just, I'd like to type return null at the bottom here, and we will replace the null for the actual return value later. So the first thing we want to do is, for our BRAP, we have different faces. So we want to find the center point of each of those faces. And from those, we want to find the maximum and minimum so that we can find the height of the BRAP. So I'm just creating a new list of points, calling them centers. And new list point 3D, just an empty one. And then we're going to use a for each loop. So in the Rhino BRAP class, you can find, or it contains, like we did for our level, we created a list of columns. And likewise, the BRAP have a list of its faces. So we will run through these. So for each, parentheses, and BRAP face, which is the class of the faces, and just call that f in b, which is the input in this function, which is a brep dot, and then you can scroll down here and you will find faces. So this gives access to the list of faces. So for each face in the list of faces belonging to this brep, we want to find the center points. So centers.add. So we want to add the center point to our list of centers. And we have, I think you used it with Bungie yesterday, which was the area mass class. So the area mass properties. And this has a method called compute. And it's the face we want to compute. And we want to find the centroid. So that returns a point 3D, which we will add to this list. So we have all the centers. And next we want to sort these centers. So I create a new list. And before we can do that, we will use the link queue, which is a language which you were introduced to by Bungie yesterday as well. So I have to add this here to be able to use it, and that is just system.link queue. So this will enable us to do some quick and easy sorting instead of having to create several for loops. So the list that I want to sort is this one with centers, because we don't know the orientation of the faces, so we can't be sure which face has the lowest and highest center point. So we want to order those. So type order by, which is the link queue function. And inside here, we want to create this lambda expression, which defines what we're going to order it by. So our variable in that is going to be a point. You can type anything here. It could be X, it could be C, it could be anything. So I'm using a point or PT. Then you type equal in a triangle bracket. And then it's our point here dot, and we want to use, this is a point 3D as you can see, and we want to use the C value to order it. So did you manage that, or are there any questions? And finally, we want this, as you can see now, this is a T element. We want to make it to a list to be able to use it. So just add that finally. Okay, so then we want to find the height of it. So double and the height of the brep equals 2. And then we know that we have this list is sorted in an ascending order. So we want to take the final point and square brackets the axis items. And in Python, you can use -1, but you can't use that in C#. So we have to use sorted centers.count, which is the number of elements, -1. So that is the final element, since it's starting at 0, the indexing. We want the C value, and we want the C value of the first element, which is the lowest one, dot C here. So this will give us the height. So it will take the C value of the highest point or the highest center of the faces and the smallest value of C. So we can then find the number of stories, which is the total height of the BREP divided by our wanted floor height and the whole number. So if it's 4.7, we just want to allow 4 heights. So we can do that by using this int here, which will return the double, because we have a double here, we have a double here, that will return a double. But if we convert it to an int, it will just take the whole part of that number. So meaning that even if we have 4.9, it will still return 4. So that is what we want. So I'm just dividing the height by the floor height. So that will give us a whole number, and that is what we want to use. So we have found the height. So the next thing we wanted to do was to create a surface at each height. So the first thing we want then is a list of planes, or plane. We will call that planes. That's a new list of planes. Since we're going to use the BREP plane intersection, we need every plane at the different heights. And then we will create a unit vector just to show us the direction of where we want to move or translate these planes. So unit C equals new vector 3D and the coordinates, which are then 0, 0, 1. And we're going to loop through all the elements or the number of stories. So a for loop, int I equals to 0, where we will start. And we should have a loop which is smaller than the number of stories that we can have, because we don't want any planes going outside our BREP. And we want finally just an I++, curly brackets. And then we have a single plane. We'll create a new plane. So a new plane. And you can see the constructors here. So we're going to use the one where we have an origin and a normal vector, which is going to be the C vector. So the origin is going to be just the, we need a new point. (3D) by 3 coordinates, and the unit vector, which is just the unit C that we created. And the coordinates for that point should be the centers of the the centers of our bottom face, or bottom surface. So we will just create the factors here to make it a little bit easier to see. So the x0 is the sorted centers 0, and the x values are the lowest center point on the BREP surfaces. I'm just copying that 2 times because we want y and c value. So you can just change that here as well. So we have x, y, c. So we can use them here. x0, y0, and finally z0. But for each time we run through a level, we want to increase the height. So I times the floor height to move the plane up at the floor for each time we run through this. So this will give us a list of planes with the plane center in the center of each surface. So the final thing to do then is to use these planes and the BREP to find the surfaces. So we will create a new list of B-reps again, which is the surfaces we're going to use. Just calling that surfaces, and a new list to initiate an empty list. And then we're going to run through each plane. So we're going to use the for each then. So we're not going to do any operations or change anything in the list, so we can just run through it and get planes. So it's the planes that are in the list. So calling that plane in planes. Or you can even, if you want to save time, just use the P. So the first thing we want to do is to, or show you here, for this method, we have the Rhino command here, and this is the method that we want to use, an intersection between brep and a plane. So this is the method, and as you can see, it takes a brep as an input, a plane, so we have a list of planes, we have the brep, a tolerance, and then you have something here called out. I'm not sure if you've seen this before, but it's a keyword that will pass out the information. So we can try to use this, see what happens. So Rhino, to find this, you have to type rhino.geometry.intersect, and then .intersection, so it's a little bit inconvenient to use. And you can see if I type period again, you have different intersection methods, and we are looking for the brep and a plane. So select that. If I make a bracket here now, you can see the input, a brep, a plane, a tolerance, and then you have the outs. So so this Rhino command that you looked at yesterday can be found. So you have an intersection class in the Rhino.geometry intersect in the namespace. Then you have the intersection, which you were using yesterday, and then you have the brep plane, which finds an intersection. And so if you're going to use this several times, because we have, as you can see in the top here, we have these already here, which you can use, meaning that if you have Rhino geometry, you can just type brep anywhere and it will recognize it because you have referenced it here. But it doesn't have the intersection thing because we're just using it one time, so we don't actually save any time by using it here. But if you know that you are going to use it, you have the namespace here, so you can just copy this, make it here, and then if I go back to the method now, you see that this becomes gray, so I don't need it anymore because I typed it at the top here. So if you're going to use something more than one time, you can place it there. But for now, since I'm just using it here, I will just do it like this. So the input again then is the brep. So a plane, which was just the P, which we're looping through, a tolerance, just type 001 or something. And then you have the out thing. So we need some parameters or to assign this to in order to be able to use it. So, and you can see that the output is an array of curves and an array of point 3D. So I need to create that before I can use this function. So I will just create a curve array, name it curves, and I can just use a semicolon. I don't have to assign anything more to it. And I will do the same thing for a point 3D. So this is kind of inconvenient with some of the Rhino commands, but there's no way around it as far as I found, so we just have to do it. So creating an array for the curves and points. So now I can use the out keyword and assign this output to the curves. And I'm doing the same for the point out there. So this function now will find the intersection between the BREP and our plane, and it will give the output as some curves and points to these arrays here. Are there any questions there, or should I continue? It's quite dirty, this expression, but also very useful. So if there's any question, just tell me, and otherwise I will copy the whole code, of course, when I'm finished. No, okay. So for now, we just have the curves representing the intersection between this BREP and plane, but we want a BREP or a surface. So we have to create that. So again, we have another method, which I can show you that we're going to use. And it's this one. We want to create a planar BREP, which is some sort of surface. And there you have an array again that will create a list of curves. We have that. And we can just set the tolerance. So surface equals BREP dot, and I want to create planar BREPs. And here you can see the reason I have an array here, you can see it's needed here because it's the output. So create planar BREPs, and the input is the intersection curves that we found and some tolerance. I can add another 0. So I'm interested only in the first surface here, and I know that it will be only one since we have just a BREP and a curve. So from this array, I would like to just get the first one. So surface 0. And I want to add that to this list of surfaces. So surfaces dot add this. So for each plane, we will find the intersection curve by this function, and then we will use that curve to create a surface, which we will add to this list. So we now have a list of all the surfaces at each level from the planes, and then we will just return those surfaces. So this method then will give us the surfaces. So I will copy that for you. So were you able to make it? That's the question. Won't these planes overwrite them for every loop?
What this planes override for integer number of new plane?
You can hear me now? Yeah, sorry about that. I quit the meeting as soon as there was a critical question. So I'm back now. And as Ukko said, he will get, you need to add this plane here, or you need to add that plane to the list, because if you don't do, you will just create a new plane for each iteration, but you won't use them for anything. So before we create a new plane, we should add what do we create here to this list outside the loop. So I will copy this and give it to you.
Just one comment from me. When you are copy pasting the code, sometimes when you are building the solution, there is unexpected character showing off. Just find those lines by double clicking at error list in the bottom and just delete this empty line, because it seems, I think, when you are copying from the Teams to Visual Studio, then unnecessary bracket is appearing, which I am not sure why. Yeah.
Okay, so we have our list, function, so we can test that to see if it's working. And that will also let us build our solution. So if you just scroll up, I can just close this to make the code smaller, and the create building. So I will create a list of brep, call it surfaces, and I will call on this function now, which you can see here. And the input is a brep, which is our boundary. And we have a floor height, which is here. Like this. And then we can finally output this. Since we have a generic output, it doesn't really matter what we put there, so we can test it. So we can then just do the da.set data list, and we need 0 and or surfaces. And maybe at the top here, I made it as an item at line 47. So the generic output parameter, so just change that to list before you run it. So the code now should only return some surfaces. So we can try to build it, see if it's working. Succeeded, great. So I will start it in Rhino. Okay, so I will use this box corner to corner function here in Rhino. I will just set the first corner point 0, 0, 0. The second corner point, let's say it's 5,000, 4,000, 0, like this, and a height, something like this. So that is our brep. So first of all, you should just check that you have your components there, 2 components. So I will just drag them onto the canvas. And if you create a panel now, like I mentioned earlier, I won't assign any input here, but you can see by default you have a value. So 300, 30, 30, 500, 500. So this is a nice way to save yourself some time by creating the 5 parameters. You can just have some default values there. You can plug it straight into here. And then we need a brep. So I'm just searching for the brep container, right-clicking that, set one brep, set it there. So it's in Grasshopper reference now. Plug it in, And what do we have? We have some surfaces. So I'll just hide the brep. And you can see all the surfaces that we have within our building class now. So if you change the height now, by default, it was 300. So let's make a slider from 300 to 600. Input that here. And you see that we changed the number of floors. So we can go to the front view, maybe it's easier to see. So the green line here are the floors or the surfaces. And as you can see, no matter how far we change it, it won't go above the top line there. So it seems like this is working. So I will just close or stop debugging it again. And we have our first surfaces, yes, and then we can start on the second component, and we can okay. Did somebody not manage to run their solution, or are there any problems, or did you make it? Okay, so just raise your hand if you manage to get this surface function working. 1, 2, 3. Some of you, that's nice. The rest of you, well, either you're shy or we can help you. It's no worries. We have a lot of time. But let's make 5 minutes then. You can try, ask if there's any questions, and we'll start again at 11:20. Okay, I'll continue. Quickly, just Camilla, sorry, question. If you go to the top of the where you assign the output in the component again, did you remember to change this to a list? Because I used item initially because we're going to output an item of a building class, but since we're testing it, I'm using a list since this is a list of surfaces. So that might be the problem. If not, Marcin will help you and I'll continue. So we have the surfaces. Next, we want to create the grid of columns, which you can use. So before we start, try to make an illustration for that as well. So the idea here is that you have the surface, and as we tested now, it was rectangular, but that will not always be the case. So you can have some arbitrary looking surface like this. And then we want to find, for simplicity, we're going to use the global Cartesian coordinate system when assigning the columns. But you have this boundary of the surface, which Marcin showed you on the first day on Rhino, I think, where you have these trimmed surfaces. So for instance, for a circle, the domain from 0 to 1 of the surface will go outside the surface. It's I can maybe open Rhino and we can do it after to launch the component itself. I think it's important to know this. So I'll just open Rhino to show you. So I will just create a surface from corner to corner. So this is a rectangular surface. And then I will have a circle like this, and I will have to make that circle a surface. So you don't need to do this, it's just to illustrate it. I will reference those in Rhino or Grasshopper. So surface container, and I will just set multiple ones because I want them both like this. And I will have a component called evaluate surface. So I will take in that surface and I will evaluate it so we can get the point, the normal, the U and V direction, etc. So like we did for the line on the first day of Rhino or in Grasshopper, we want to reparameterize it. So we want the domain to go from 0 to 1 instead of 0 to its length because it's easier to work with. And I want to use a component called an MD slider. So it's just like a slider from 0 to 1, but it creates like a UV coordinate instead of just a 1D. So you have coordinate here and there you just have a point. So I will use this because it's the surface it's in 2 domains or 2 directions. So the center point now you will see in the middle of both surfaces. But if I go to the start point, here you see this will be in the corner and be on the surface, whereas for the circle, it will be outside. So the surface domain of the circle will not always be inside the circle. And that is why we want to create this component or function which finds the start point or the lowest point of the domain and the length in the direction, the maximum value. And then we will assign a column grid in this domain to make sure that we get everything. And furthermore, we don't want the points outside, so we have to implement some kind of control to see what points are actually on the surface and which are not. So there's 6 minutes till lunch, but I think we'll just start on it and we'll see how far we get. And if we're not finishing, we will do it after lunch as well, before Marcin will finish things off with you. So we go back to Grasshopper or Visual Studios. We had our first function or method here. We'll create a new method beneath it. Again, it can be private because nobody else is going to use it outside this file. So again, a list. This time it's going to be points, so point 3D, and I will call it column grid. So the input here is going to be the surface, so a brep surface, a double, which is the column division in X direction, the column division in Y direction, and the column offset, just so that we don't get the column outside in the beginning. So that's going to just be, or what did I call it here? So the column offset, yeah, we can call it the column offset. Okay, again, it will be red since there's no output yet. So I will just do it like this to get that red one away. Okay, so the first thing we want to do is, again, this is surface of BREPs, and by definition that is a list. So we will create a surface here, call it surface, and it will be, or just make an assert to indicate that it's plural. So surfaces dot surface. So it's just one here, but we have to do it like this anyway. So this will get the first element from this brep faces as a surface to work on. And then we want to do exactly like I did here with the reparameterize to make it from 0 to 1. We need to do that in Visual Studios as well. So I just take the surface. It has a method called setDomain. It has two domains, so you can see, zoom in, not sure if it makes it bigger, but the direction, which is either 0 or 1, meaning the U and V domain, and then the interval, which is a class. So I will start in the first direction, and then I have to create a new interval, which is like the domains that we did in Grasshopper previously, and that will go from 0 to 1. Oh. And a semicolon here, and I will do exactly the same thing in the other direction, surface dot set domain from 1, and then a new interval again, going from 0 to 1. Okay, so we have our surface, we have a domain. Just this parenthesis here. And then we want to find the corner points of this domain. So the maximum and minimum points, so that we know that the entire surface will be inside of this. So we want point 3D, just calling it P1, and then we have a surface, and it's working exactly like the evaluate here. We want to have a point at this surface, and the point should be at 0, 0. So this will be the first corner point. And I will just copy this, just save some typing. 4 times, you want the 4 corner points of that domain. So P2, P3, and P4. The second one can be 0, 0, then 1, 1, and then 0, 1. So we have the 4 points, and I will create a list out of these. So point 3D. Call it vertices of the domain, and I will have a new list. So this is probably new. So since I already have some points here, I can assign them to this list directly by using a curly bracket and then just type in these points. So instead of using create like an add function, I can just do it here. So P1, P2, P3, and P4. So this list will now contain these 4 points here. And then again, we need to use the link queue because we want to find the minimum and maximum x and y values in both directions. So we want the x min, we want the y min, we want the x max, and we want the y max. So again, I'm going to use the link queue functions to sort this. So we have the list here, and now we just want the minimum value. Then we need to create a lambda expression once again. So a p, which is the parameter. Again, it can just be a point. It's entirely up to you. And then the x value of that point. So the minimum x value of these points will be assigned here. And we have to do the same here. So but there we want the minimum y value. Here we want the maximum x value. So you can use the maximum sorting here. The same here, but this time the y again. So just double check that this is correct because it's easy to make some small mistakes there when you're just copying and pasting. It's easy to oversee. So just take a couple of seconds to check this, and I will continue. Okay, so, and finally, when we have this in the bottom corner here, let's go back to the picture. When we start placing our columns, we want a small offset so that when we're checking for the containment, say that it's a perfect square here. If this point is starting in the 0, 0, it won't be found as inside the surface, so we will miss the first row of columns. Not sure how much sense that makes, but so we want to actually move it a little bit. So we want to move it a little bit. I can't draw. So we want to move it in here by the distance of the column or the column distance. So I'll just add the column offset here to make sure that it will be inside the surface. Not very important, but just a small detail to make the column grid better. So we have the maximum and minimum values in x and y direction, so we can find the distance. So x distance, simply x max minus x min. And the same goes for the y, so just copy paste y, y, and y. So we know how long our domain is. Okay, any questions so far? Or I see that we're past lunchtime, so maybe it's time to stop there and continue. Are we hard on them today? Fine. Is it okay if I use 5 minutes more, or do you want your break now? Yeah, raise your hand if you want 5 minutes more. Okay, there are some hands, so we'll continue. Okay, so we have the distances. So now we want to create a plane or a start point. Or now we can find the number of divisions that we can get in both directions, like exactly the same as we did for our height and the number of planes. So that will be an integer as it's a whole number. And it will be a division in x direction. And again, we use this conversion to an int, which will take the whole part of the double and make it an x distance, which is the entire length found here, divided by the column distance or spacing, that is an input factor. And since we are starting on 0 when we are counting, we have to add 1. Exactly the same again, converting to int, y distance over, sorry, it should be dx, like this, plus 1. Okay, so we have all the information that we need right now for the spacing, so we can create a new list again, an empty one of points. I'll call it column centers, because this will contain all the centers on that surface. And it should be a new list point 3D. Okay. And then to make this control to see if it's within the surface, there's no function in Rhino that uses the surface as it is. We have to convert it to a boundary edge to make it work. So again, a little workaround there, but we will try. So use the method brep edge, which was the one that we looped through earlier. And you need again an array. We will call that edges. And surfaces, which is the input, edges dot to array. And I will create a new list again, which would be the curves that we're going to use later. Edge curves, new list of curve. So then we will loop through all the edges here. So for each, going through everyone. So a brep edge is the class. We'll just call it E for edge. And edges, which is this array. And we will add all the edges to this list of edge curves. So we can do it in 2 lines. Oh, no, we should just do like this, edge curves, which is this list dot add. So we want to add something, and the thing we want to do is we want to add this brep edge. But to do that, we first have to convert it to a curve. So E, because this is now a brep edge, sorry. So we want to convert that to a NURBS curve, which can be contained inside here. So we now have a list of these curves. Then again, we want to create a continuous boundary curve and not just a set of curves. So again, curve, Rhino tells us that we need to use an array, and then I will call that boundary curves, and that will equal to, and we will use a curve method here, curve dot, and you have join curves. And the input here, as you can see, is the input curves, which are our edge curves. Okay, so I think that's a good place to stop for a break, and we will continue at 12:30, I think. So if there's any question, we will be available mostly through the lunch break, and then we will start up again at 12:30. See you then. Okay, welcome back. I think almost everybody here. So I think we'll just start. So let's just make a quick recap of what we did before the lunch. So for this create building component, we made a method for creating the level surfaces. And now we are working on a method to create the column grid. So again, I'll just open it here. So now we have set a domain, which gets the length of this domain in both directions. We have found the edge curve here from the surface. And the thing that are left to do now is simply to get the points that are inside the surface and not those outside. So we have the column grid component, and the final thing that we did before the break was to get the boundary curves. So if there is a surface where we have the situation of having something like, let's see, we did on Monday for the hollow sections, something like this. And just set those curves. And then we use the boundary surface component. Don't have to do this, it's just to illustrate my point. You have this surface here with the hole in it, meaning that this component or this curve here or array of curves will join first the outer curves and then the inner curves. So here we will actually have two boundary curves, one internal and one external. So we want to make our function work even though there is an internal hole here, meaning that we don't want to place our columns. Say that we have a hole here. We do not want any columns inside of here. So to do that, we have to create a list or a loop where we create the points. And again, I can go back. We want to create points in this direction and this direction. So like Marcin did it yesterday, this is like doing the graph in the Grasshopper component. So we have a series of points here and a range here. So you want to do for this instance here, we want to make every point with the x coordinate of say 0. Then you want x0, 0, 0, 0, 1, 0, 2, 0, 3, and so forth. Then we go to the next one, which is 0, 0, no, 1, 0, 1, 1, 1, 2, and so forth. So to do this inside Visual Studio, you will need to create a nested loop or a double loop. So we'll do that here. So first we will do the x direction. So a for loop where we call it the u direction here since we are working in the UV domain of the surface. So we will start at 0. We will have from u to, and we will have the number of divisions in the x directions that we found previously here. So just copying that. Oh, sorry. Control C. And just u plus plus, which is equal to writing plus equal 1. So the plus plus is just a shortcut. If you want to increase the counter by 2, you can write plus equals to 2. So just to show you how it's working. And then we need a square brackets. And then again, this is just in the x direction or u direction. We also want the v direction, so we have to create a new loop. Again, brackets, int v direction equals to 0, v smaller than div y, which is the number of divisions in the y direction that we found previously. And again, it should increase by 1 for every iteration. And again, brackets. So we're going to use quite some loops here. So now we want to create this point. So again, back to the PowerPoint, we will create this point, then this point, and this point all the way. And we will go through like this. So we will create the point. So just a point 3D with the coordinates of u point 3D, and the x min value plus, and then because it will start at 0, and then we want the counter times dx. So the first iteration, it will be in the domain 0, 0, or the starting point, and then for each iteration we will move one step in the x direction, and the y or will be the x, that will be the same. So it will be y min plus, and we have to do the same, v times dy, and the set component will be the same. So we can just use this point, for instance. So p1 dot c, like this. So that will be our point, or our point, and then we have to check if we want to add this or not to our list, and we should only add it if it's inside our surface. So assuming that now we don't know how many holes we have here and then how many boundary curves, so we'll create a new loop for, and I can use I this time equal to 0, and we want to run this loop for as many iterations as there are boundary curves. So meaning that if we have more boundary curves on our surface, we want to iterate more. So we can use boundary curve dot, and as you can see here, we have to use length instead of count, which is exactly the same as count as we used previously for a list. But since it is an array, we have to use the length. And I smaller than, and again, I plus plus. Curly brackets. So for each boundary curve, and I forgot, we want to create some, I can do that afterwards. We want to check if the point is inside or outside that curve. So if we have the boundary curves, I, because we're looping through these now, and we can use a curve method named contains. You can see it here, and the input that is taking is a test point, a plane, and a tolerance. So the point is this one. Oh. And we need a plane. We don't have that yet, and we need a tolerance. So just something. So the plane should be again in the surface, and we have a start point here, so we can just use it to create our plane. Yeah. So just type plane, and you can call it plane again. We need a new plane. Let's see the constructors. We have some to choose among here, and we'll choose the one with just an origin and a normal vector. So the origin can be the P1, which we already have, and we need a new vector, which can be a vector 3D from 3 points. So 0, 0, 1, so a unit vector in the C direction. But there we are, and this is not, yeah, this is just, yeah, I can show you this, the contains method. It's here. So curve class, you have the methods, you have the contains, and we are using this one. And as you can see, it's returning a point containment value. It's not returning a bool like a true or false, and that is why we get the red line here. So to fix that, we have to check if it's, first of all, like this, and then this should be equal to, and you have a point containment, which this returns, and you see the proposal here, point containment, which is a class again, and we can select dot, so we want to check if it's inside or outside. So let's choose inside. So if this point is inside this curve, this will be true. And then we will enter this bracket here. And here we want to simply say inside. Oh. So we hold on for that. Okay, so we will go here again. And what we want to do is, since there are several curves, say that we have a point here. Okay. So if you first looping the first iteration, we're checking this curve. And if it's inside this curve, we will add 1 here. So we will have an int inside equals 0. So if it's inside here, we will add it inside plus plus or 1 to that. And if it's not outside, nothing will happen. And we will have something here called outside. So I'm creating that as well. Or just all. That's better, I think. So all. So no matter what, we will add 1 to all when we're counting. So for this point, for the first iteration, we're checking if the point is inside this curve. And that is true. So we will add 1 to the inside here. So that will be 1. And we will add all, also add 1. So both will be 1. And when we run through this curve, it will not be inside this curve. It will be outside. So nothing will happen here, but this will still be added. So we will have 2 here, 1 here, meaning that the point is just inside 1 curve, and that is what we want. So then we create a new statement here. If inside is equal to 1, then we want to add that point to the column centers. Because if you're looking at this point here, for the first iteration, we are running through the outer curve. It will be inside that, so we will add 1 to the inside, and it will also be inside this one in the next iteration. So inside will be equal to 2, and then we do not want to add our point. Like this. Okay, so if the point is inside just one of our curves, we know that it's inside the surface, and we will add it to the column centers. And finally, we will just return our column centers. And there was a comment earlier about forgetting to change this from null, so just remember that. And I see you can also remove this all. We don't actually need it. This was just for illustration purpose. So this is the final code. I'll just give you a couple of seconds to finish that, and I will upload it in the chat for you to have. So are there any questions, or should I continue? Okay, so we can test this now if it's working. So if we go back up to our solve instance here, from previously we had the surfaces. So let's check now if we can get the center point or a column grid on one of those surfaces. So for now, we can create a list of points. With column points, and I will call the column grid method. The inputs were a boundary surface, so let's just take the first one from here. as a single element. Spacing, we have that, dx. We have dy, and a column offset, which can be the column diameter divided by 2. Okay, since it's the center point, we can divide it by 2. And then we can output this and see what happens. So try to build a solution. Build succeeded, so I'll run it now. Okay, I will create the, So I will create the box again. Just the simplest brep to create 0, 0, 0, 4,000, 5,000, 0, some height. Select this. Oh, still getting the surfaces. So what you can do while you're in Visual Studio and debugging, if I press pause now and go back here, if you hold over a code line at the left side of it, you will see a small, this run symbol, run execution to here. So if I press that now, I will be sent back to Grasshopper. And if I right click and recompute it, it will stop before assigning the output. Or should it please do that? Oh, okay, it's because I have another file open for the illustration purposes. I just have to close it for it to work. Oh. Okay, so I just have to restart it. So if there's any questions while I'm doing that, feel free to send it to me or Marcin privately or in the chat. And if you manage to create the column grid method, please raise your hand. 2, 3. That's very good. Yeah, that's very nice. So you can hold the course next year. So I will try and I will run it. I have set the column points as the output now. We'll see if we can't make it work. Oh. Yeah, okay, so have to restart it again as an administrator to be able to do this. So Visual Studio, the right one. Okay, let's try again. So point or box by 2 points. The reason why I'm doing it with the coordinates now is to make sure that I get a big enough box with the preset default values for column divisions and the building parameters that we created. So brep, set one brep to reference this one, and these two, this one, and there we have points for the center columns. As you can see now, this distance here will be equal to the radius of the circle, so that we get the first column row here. If we had set it to 0 initially, then we would miss this and we would have some spacing here with the other column. And the reason for us having this one is because it doesn't add up exactly. So right now I'm using a column spacing as a definition of creating this grid, but you can also use like a number of columns that you did in the first day, where you just set a number and then you can divide to find the distance. So it's up to you really. So it's multiple ways of doing this. Right now it's 500, so we can create a slider from 300 to 600. Let's see if it's working. There we are. If I change the column spacing in the X direction and the Y direction, we get a denser, less dense grid. So seems like this component is working also. So I will kill it. And we have everything we need for to create our building. So if you go back to Visual Studio, we have our input and we now want to create a building. So we made a building class earlier this morning. So we will now initiate that. So type building, and we will call it just a building, and it will be empty initially, just to show you multiple ways of doing this. So this is exactly what we're doing for the point 3D, the brep. We're just creating an instance of this class that we made for ourselves. And maybe we want to give the building a name. So I have the building, and I have some properties here, which you can get in set. And the name now, let's call that my building. Okay. And the next thing we want to create is the surfaces, which are here. We want to assign this to the building. So yeah, one more thing. I think we can. I can show you these yellow boxes and red boxes that you've seen in Grasshopper. If something's wrong, how to make those? If you want for your own component. Here, for instance, we have a building. So say that our building should have at least 2 slabs. It should be a floor and a roof. So if there is one slab, it's not really a building. So, but the